Signal Conditioning Part 1, and this series of films is about deflection bridges, or indeed it's to convert a change in resistance to a change in voltage. Because if you have a sensor like this, that could be a temperature sensor, pressure sensor, whatever, and you want to use this somewhere on another location. So this is where the signal is to be used. Let's say that there is some distance between the two. Well, it's not very easy to relocate this sensor to another site, because then you really take it out of the environment where it's measuring and where it's doing its job. So what you really want to do is to convert the change in resistance to a change in voltage instead. So delta voltage. So you really want to change it to that. And to relocate the voltage is simply connecting by wires. So the voltage you measure here is the same as the voltage you measure over there. So deflection bridges is one of the tools that we use in order to change a changing resistance and convert it to a changing voltage. So first of all, the easiest trick in the toolbox is a so-called voltage divider. A voltage divider is a device where you have a power supply, and you have a resistor, and you have a second resistor. So what you measure here is the Vs, the supply voltage, and then if you measure, say, across this resistor, you can measure V out. Well, one of them must be fixed, and the other one can be variable. Doesn't matter which one, but let's say that this one, for now, is the sensor, and the other one is the fixed resistor. Let's name them R1 and R2. The current that runs through the circuit in a loop like this can be described as I equals the available voltage over the sum of the resistors. The voltage at the output equals I times the resistor that we measure across, I times R2. And that, if you take the I from over here and into this equation here, it becomes Vs over R1 plus R2 multiplied by R2. Or if you like, if you can sort it a bit, Vs R2 over R1 plus R2. Now, and that is V out. So that results in V out being a function of R2. So the change in the voltage is a result or due to the change in resistance R2. So we have done exactly what we wanted to do. One problem here is that if we look at the, let's say, time, and we have Vs, the supply voltage, let's say that the resistor here, this one, varies a bit with time. The voltage here, V out, will also vary with time, but it will vary about here, somewhere in the middle. What we really would like would be to have that shift in voltage down here instead. So if we can make a device that takes this change in voltage from up here to down here, that would be better. That's because when we, for example, digitalize this signal here, we have to divide the available voltage into equal steps. But if we shift this one down here, we can do it with a much better resolution. We can simply digitalize from there to there. Also, if I amplify this signal like this, for example, it's easier than if I amplify when it's located where it was. So if I amplify it when it's up here, I have to amplify the entire range from here to here. So therefore, I would really like some tools to shift this one down to the lower part here. And that is done by having two voltage dividers. Let's first draw the first one. The only difference is that I now drawing the resistors in a diamond-shaped way. So this is my R1, this is R2, and this is my sensor. Now let's call this point A here. Let's also add a second set of resistors like this. And here is why I drew it in a diamond-shaped way. R3 and R4. Now, if all the resistors are fixed apart from R2, I hope that we can make this voltage that we looked at on the previous page to shift down to this area here. Now let's look at the mathematics behind it. We already learned about the voltage divider, so VA, the voltage on here on point A compared to down there. Let's ground this one. VA, if I measure the voltage from there to there, is the same as the voltage across R2. It's R2 over R1 plus R2 multiplied by Vs, which is the supply voltage. Same for VB equals R4, R3 plus R4 multiplied by the supply voltage Vs. Now, if I want to measure from A to B, so like this, plus here, minus there. So I place a voltmeter between points A and B. Then I get that VAB equals VA minus VB. And that is V supply R2, R1 plus R2 minus R4, R3 plus R4. Now, what I have here in this part of the equation, I have the original equation that I had on the last slide. Now, this one is the new part, and there's a minus sign between them. So, and these are all fixed components. This is a fixed component as well. So I now use this part to shift the voltage to its lower region here. So I use the second part of the equation to shift that one down there. So the voltage changes from here to here due to the second part of the equation, this one. So this is very popular in instrumentation, for instrumentation purposes, because we now have a voltage VAB which is a function of R2. All the other components are fixed, so it's a function of R2. So the voltage between A and B is a result of the change in the resistance R2. And that voltage between A and B, I can use that voltage on another location simply by using wires. So I can use it over here, for example, simply by using connecting wires.